All right, for 11.2, we got arcs and chords. Apply properties of arcs and apply properties of chords. Those are the two objectives. All right, so if you remember from last section, a chord goes through it. So it starts here at A, goes through B, and it stops on the circle. An arc is going to just be the edge of the circle that we want to talk about. All right, so we got a central angle. A central angle is an angle whose vertex is the center of a circle. That's your first buzzword. And we'll see a diagram here in just a minute. So a central angle is your first buzzword. It is an angle whose vertex is the center of a circle. An arc is an unbroken part of a circle. Maybe we didn't talk about this last section. For some reason, I thought we did. An arc is an unbroken part of a circle consisting of 2 points called the endpoints and all the points in between them. So copy down this diagram, a minor arc versus a major arc. The central angle, this is what they talk about a central angle. This is an angle that's made from the center of a circle. It goes A to B to C. Angle B, since B is in the center, it's a central angle. Vertex is at the center of a circle. An arc, all the arcs down here are drawn in red. This is a minor arc because it doesn't take up more than half the circle. Points are on the interior of a central angle. So these are the arc, a minor arc. The measure of a minor arc is equal to the measure of its central angle. In circles, on triangles, our magic number was 180. In circles, it's going to be 360. If I start here at C, and I measure all the way around the circle, I get 360, which kind of makes sense because let's zoom this in and let's pretend that this line is all the way across. If I measure with my protractor, if I lay my protractor out straight, start here at 0, I count all the way, straight lines make 180. Well, I've only gone the diameter, so I'd have to go the other way, and there's another 180. That's why circles measure 360. So a minor arc is just the little section between the angles. A major arc is outside the angles. So here's the central angle that it's make. The major arc is everything outside of here. So to find the minor arc, you just take the degree of the angle. And then to find the major arc, if they give you this, you have to take it away from 360 to find this. Because from here, starting at A, going all the way around it, counterclockwise, I get 360. Well, if I want to just stop here, I can't count this. Well, that's why they take it away from 360. They're taking it away from the whole circle. So to find the major arc, you use ADC, or 360 minus x. When you name, notice how they named it too. When they named this arc, they just used AC. And they were able to just put the little arc symbol above it. When they named the major arc, they had to use 3 points. Because say I wrote just AC, and I was talking about the major arc, you wouldn't know, am I going this way or this way? AC, I could go A all the way to C, or I could go A all the way to C this way. So since you don't know, if you wrote just AC, you're assuming you go A straight to C. You have to put the D in the middle, so you know you're going from A to D and then to C. So make sure that you put the 3 letters in there if you're naming a major arc. And then lastly, semicircle and major arc is your second buzzword. A semicircle is just half the circle. So it's 180. Starting here at E to G, it's 180. And that's the arc. The arc is the semicircle. This is just the diameter. If the endpoints of an arc lie on a diameter, the arc is a semicircle. And the measure of all semicircles are 180. All right, and then this is just restating what I said earlier. Minor arcs may be named by 2 points. Major arcs and semicircles must be named by 3 points. All right, so let's do an example. The circle graph shows the type of grass planted in the yards of one neighborhood. Find the measure of arc KLF. Notice that this has a little bit of curve to it, so it's not a line. It's supposed to be an arc. All right, so what I need to do is I'm finding the major arc KLF. So to find major arcs, I take 360 and I subtract the minor arc. Well, if here's the major arc, the minor arc is going to be here. It's going to be KF. So minus the measure of KF. But this problem is a little tricky because what you have to do first is notice that all these numbers are in percents. If I added all these up, I would get 100, which makes sense because all the percents make up 100. But a circle makes 360, so I need to find out what percentage, if this is 20%, how much of 360 is 20%. So what you would do is take 360, you're going to have to do this for every section. 360 times 20%, 20% as a decimal is 0.20. You multiply that and you get 72. Okay, so this degree right, this angle right here is 72 degrees. All right, let's squash this, get it out of the way. Now I want to find the angle degree of this one. How much is 8% of 360? So 360, I want 8% of it, so I multiply it by 0.08. When I change 8% to a decimal, I move it 2 decimals to the left. There's a 0 in there. 8% of 360 is going to be 28.8. All right, so let's zoom this in. All right, you're going to do the same thing with the Bermuda, with the 7%. Bermuda was 7%. You're going to multiply 360 by 0.07, and you're going to get this to be 25.2. So we'll squash this. So I've got these angles. Now to find the measure of this angle, what you could do on this problem is you could just take 65% of 360 and just be done with it. But they want us to do the formula, the 360 minus the minor arc. They have the 65%, so you could just do 360 times 0.65. But let's play along with their games and let's figure out what this total is, the minor arc. So I take 72 plus 28.8 plus 25.2, and I get this is going to be 126. All right, now to find the measure of KLF, now that I know this angle, F all the way to K is 126, now I can figure out what the rest of this is. So I just take 360 minus 126, and I get 234. So the measure of arc KLF is 234. All right, adjacent arcs. This is your next buzzword. Adjacent arcs of the same circle that intersect at exactly one point. RS and ST are adjacent arcs. So notice how S is the common point between them. They're adjacent because they're touching. That's what it means. If I drew this circle and I said this was RS and this was PQ, these would not be adjacent. They are adjacent because they're touching. All right, and then we got arc addition postulate. This is hopefully going to start making a little bit of sense because to find the measure of ABC, if I've given this and I've given this, you just add it. It's just like a line segment. If this is 2 and this is 1, from here to there is 3. You just add them up. Same idea. If this was, let's say, 60 degrees and this was 30 degrees, to get from here to there, you just add them up and this would be 90 degrees. The whole thing is 90. That's just an example. That may not be 90. We'll do an example here that will be, maybe. Okay, so simple. The main idea is that you add this, and you get the whole thing. So let's find the measure of arc BD. So here you're going to have to do a lot of adding and filling in everything you know. So that's what I would start off by doing. So let's zoom this in. Again, our magic number for circles are 360. I want from A all the way around back to A to be 360. Now notice how I've got some lines going all the way through the center here. So EB is a diameter. AC is a diameter. FD is a radius because it does not go all the way through. All right, so I'm going to use the fact that this is a diameter to figure out what this is going to be. Because I know AE plus ED plus DC is going to equal 180. So basically, I'm just going to do 97.4 plus 52, figure out what this is, subtract it from 180 to find DC. So DC is going to be 30, I'm going to take 180 minus 97.4 minus 52, and I get CD to be 30.6. degrees. All right, so now I'm going to take, again, the fact that this is a radius, I can take this to equal 180. It's a straight line, 180 degrees, so this is going to be 82.6. All right, and we got our last line. This is going to be a straight line. If this is 82.6, this is going to have to be 97.4. Which, if you're a pro at chapter 4, you remember that these are vertical angles. Notice how they make the X, so this was going to be the same thing no matter what. So 97.4, 82.6, 97.4, 30.6, 52. If I added all 5 of these numbers up, I get 360, which is perfect because that's what the angle is. So I need to find the measure of arc BD. That is going to be BC plus CD. BC was 97.4. CD was 30.6. Do a little plussing, and I get 128 degrees. Okay, so the measure of arc from B to D is 128 degrees. All right, with a circle or congruent circles, congruent arcs are two arcs that have the same measure. In the figure, ST is congruent to UV, the arcs are. So again, because this angle is the same as this, they're both X, this arc is going to be the same as this arc. So if I put an equation in here, like 3x, and I put over here 2x plus 5, I can set them equal to each other and just solve. All right, so here's some theorems. Go ahead and write this table down, please. Theorems and hypothesis and some conclusions. Basically, like I was saying over here, if I've got the angles are congruent, we said that the arcs are congruent. Now we're going to say that the chords are congruent. So congruent central angles have congruent chords. Because these have the same angle, they have congruent chords. Congruent chords have congruent arcs. So because the chords, the blue chords are congruent, the arcs are congruent. Congruent arcs have central angles. So basically, the main idea here is that if I've got any of these 3 things stated in common, if the arc, the chord, or the angles are paired up with the opposite arc, chord, or angles, they're all going to be the same. You've got all of these. Notice how these are all different. This is saying chords are congruent, arcs are congruent, angles are congruent. So if only one of them are matched up with congruent, you can prove the other 2 are congruent as well. Okay, so they're going to tell us that TV, the chord TV, is congruent to the chord WS. So since the chords are congruent, their arcs are congruent. So VT arc is congruent to WS arc. So it's just, again, simple plugging things in and solving. Add the 11. Nine n equals 7n plus 22. Subtract the 7n over. 2n equals 22. So n equals 11. All right. again, that's great and all, but that's not what they're asking for. They want the measure of arc WS, which is right here. So I take WS is 7n plus 11. Put in the n equals 11 for it. So arc WS equals 7 times 11 is 77. Plus the 11, I get 88. All right, next example. We've got ray PT, again, this is the symbol for ray, bisects arc RPS, or angle, that's supposed to say angle, not arc. Angle, not arc. So I'm going to go in, as soon as I see that, I'm going to go in and write that in. So here's RPS. To show that PT bisects it, RPS gets cut in half, so I can draw little arc marks right there. Now they want us to find RT. Well, since I know the arcs are congruent, or the angles are congruent, I know the arcs are congruent. And because the arcs are congruent, the chords are congruent. So I literally just set 6x equal to 20 minus 4x. Again, when you have something congruent in these type of problems, 9 times out of 10, you're going to be setting them equal to each other. Otherwise, you're either going to be, if it's a semicircle, you're going to add up to 180, or if it's a whole circle, you add up to 360. But in 11.2, I believe almost every one of our problems, we're going to be setting them equal to each other. So I take 6x equals 20 minus 4x. Add the 4, 10x equals 20. X equals 2. Find RT, so I plug 2 back in for RT. RT equals 6x. 6 times 2. RT equals 12. All right, last theorem for us to get down. So we know from last section that tangents form right angles. In a circle, if a radius or the diameter is perpendicular to a chord, then its chord is bisecting its arc. Then it bisects the chord and its arc. The radius does. So if this forms a right angle, this gets cut in half. CD bisects EF. So if this is a right angle, I now know this is true, and I now know this is true. In a circle, the perpendicular bisector of a chord is the radius or diameter. So again, this thing is the same thing. I hate how they do this because they're trying to say it's two theorems, but it's basically the same thing. This is saying one thing, and then this basically says it backwards. If the radius is perpendicular to the chord, it bisects it. If it bisects it, then it's a diameter or a radius. So same thing. Again, they're going to tell you that this is a perpendicular line to the chord. So what you're going to do is you're going to be able to set these equal. All right, so let's find NP. This is kind of a confusing diagram. They do have the radius being perpendicular to a chord. So since the radius is perpendicular to a chord, I know that the chord gets cut in half. So I'm going to put tick marks in here. Because of this right angle. Only because of this right angle being at the radius do I know that these are congruent. All right, so let's follow their steps. It's just 3 steps. Draw the radius RN. It's already been there for you. On the problem, you're only going to be given what's in black and what's in red. This blue line was drawn on here. I left it in here because it's hard for me to draw that in with my stylus thing. So they gave you the circle, they gave you the radius, they gave you this chord, they gave you N, R, S, M, P, 8, and 9. So since 8 and 9, RM is 8 and 9, RN is 17. So I'm going to go ahead and say little r stands for radius equals 17. So if you want, you can go in and draw it in too in your diagram. Now it says use Pythagorean theorem. Well, how on earth would Pythagorean theorem help me solve this problem? Well, I do know that because this is a right angle, this forms a straight line, this is also a right angle. Inside here is a right angle. So I've got this triangle with a right angle here at 8 and 17. Oh, now I see how this is going to help me find, Pythagorean theorem is going to help me find this because I've got 2 sides of a right triangle. So a squared plus b squared equals c squared. Again, I'm going to choose 8 to be my a because it's the shorter side. 8 squared plus b squared. C squared, this has to be the c because it's opposite the right angle. Now I'm going to solve. I get 64 plus b squared equals 17 squared gets us 289. Subtract the 64 over. I get b squared equals 225. Now let's just see if I square root this, because that's what I want to do to get just b alone. Let's see if that does come out to be a perfect square number. I hope it does, because then I don't have to worry about trying to reduce it. So square root of 225 in your calculator gets you 15. So b equals 15, which is nice. Now I don't have to worry about reducing radicals and all that stuff. If it didn't come out to be 15, then I'd have to go and change that. So I'm going to go in here, change this to now 15. So ns is 15. Again, how does that help me? Well, I do know that because this radius was a perpendicular line, or perpendicular here, these are congruent. So since this was 15, this is 15. So I doubled 15 and I get 30. So NP equals 30. We'll do several of these problems in class to get better at these, but that's it for today.